Hi guys, welcome to Learn Electronics Repair. And this contraption on my desk here, this is the prototype of the bipolar and for that matter MOSFET tester. This is the destructive tester. So the way this works is using these switches you can increasingly add more current load to the transistor you're testing, and if it fails before it reaches the rated current, as you would see in the datasheet, it's either a damaged transistor or a fake transistor. Okay, when I say destructive, if you are testing a transistor and it's a good one and you use the datasheet to look up the maximum ratings for the transistor and stay below that, it should be fine. Yeah, this will be destructive to fake transistors. So we looked at this previously, we looked at the schematic, and this is a project sponsored by PCBWay.com. So the idea is we're going to upload this to PCBWay, which we see here as a shared project. That means you can order the PCBs and build this yourself. So in the previous video, we designed the schematic. You can see here, this is for testing P-type MOSFETs or PNP transistors, N-type MOSFETs or NPN transistors. It says EBC, emitter, base collector, but that is also gate, drain, source. Okay, and from that we designed the PCB layout. Now you can see it's a fairly simple layout, but it's quite a chunky PCB, and that's because we have up to 10 amps flowing through here. Okay, there's some large components like the fuse holders here, for example, the power terminals. These are the connectors where you test the transistors. Look, say emitter, source, base, gate, collector, drain, marked. Okay, and these are the connections to the load, but the load itself also has a switch on which switches between N-type and P-type. So that was a PCB I designed, but I didn't upload this because I wanted to build a prototype to see if this actually works. And that's what we're going to do today. But as part of building the prototype, I realized that I shouldn't be making the PCB like this. There's a much easier way to do it and more practical. Okay, so that's what we have today. So first of all, let's have a look at this load. Let's test it. Let's see if it actually works. I'll just show you how this is put together. So we have a bit of Vero board here. Now, these are the power connections coming in, basically, through the transistor, which you're testing. So this is where the 10 amp flows. These are the connections where you actually connect your transistor. And what I've done is, if we can probably, yeah, we can look under there. You can see we have big, thick, heavy tracks. Basically, I've put a lot of solder, filled the tracks with solder to handle the currents. This is just a rubber foot thing, by the way, just to balance the PCB. The rest of the circuit only conducts up to about 1 amp, so this is not high powered. We can see the fuses, they ended up tucked under there. They're a little bit out of the way really, so we have to unbolt this PCB to change a fuse. Not the best of designs, but that's how I did it. And then we can look at this wiring. So these are your power coming in, plus minus. This is from your bench supply, okay? And the switch here switches between P-type and N-type, okay? And if we look for the P-type, okay, the red, you see this brown wire comes to the emitter of your transistor you're testing, comes back out on the collector, and then this goes down to the switch there, okay? And when the switch is in that position, it connects the brown wire to this yellow wire. And that is the input to your load, positive, okay? You see I've actually soldered it in the middle, so the current can kind of flow both ways. It reduces the current on the wires here when all the switches are on. And then coming out from these resistors, you see we have all these red wires and these go to the switches. Okay, so these switches are single pole, single throw, okay, on or off. So as we switch each one on, it switches a resistor into the circuit, and that gives us about 1 amp. Okay, so literally 1 amp, 2 amp, 3 amp, but you can switch them any order you want. Each one is 1 amp, and the idea is you increase the load by 1 amp until you reach the maximum that this can provide, my power supply being 10 amps, or the maximum the transistor can actually handle, according to the data sheet. You'll see then the switches now. Each switch has a black wire. These black wires, one from each switch. I have 5 of them here and 5 of them there, and they all come back to the center pole of this switch. Okay, and in the P position, that connects to this black wire, which is returned to your power supply negative. Okay, and with the switch the other way, well, we now have negative coming in through the transistor, emitter to collector. So this is your NPN or N type, out on this blue wire, which you can see goes down to the switch there, and then that connects to the yellow wire through the resistor, through the various switches. Okay, and comes back out on the positive. So the polarity effectively flows the opposite way through the transistor under test and through the load, depending on the switch. This switch is about 20 amp, I think, but bear in mind you don't need to switch that while the thing is on with a big load, so you're not likely to get any arcing in the switch. These little switches are all, I think, 5 ampage. I'm only switching 1 amp. So that's how the prototype is wired together. This little PCB has 2 voltage regulators on, a 7809 and a 7909. The original one had 12 volt regulators. These are 9 volt regulators. And because I'm using 9 volt regulators, the load resistors are 9 ohm. Okay, 9 volts, 9 ohm, 1 amp. The reason I use 9 volt is to do with the power dissipation. So when one of these resistors is conducting, any of them, each one is going to pass 1 amp, and it's going to have 9 volts across it. So it's going to dissipate 9 watts. Okay, these are 50 watt resistors. Presumably, if we are testing a fake transistor, at some point it's going to go short or open. If it goes short, then the full voltage from the power supply will now pass through the resistors. My idea was that we set this up in such a way we have about 20 volts coming in, so we have 9 volts across here and around 10 volts across there, because there's going to be a bit of loss on the wiring. Okay, and with 10 volts across the transistor at 1 amp, it's dissipating about 10 watts. So we know each time we put an amp on, we get 10 more watts dissipation from the transistor. And again, we can easily make sure we stay within the rating in the datasheet for wattage. Okay, the transistors, by the way, just tag onto here, so the wires just go in, and then you can bolt them onto here. Okay, you can bolt them onto here, either a TO3 or TO220 or any of these other chunky type ones. You can easily bolt them on there. Because there's nothing else connected to this metal heatsink, we don't need to have an insulating washer under there. We can bolt it straight down. The heatsink, by the way, came from a scrap amplifier. Yeah. But any heatsink you can get your hands on, basically, that's just large enough. Okay. The fuses are to protect the voltage regulators should the transistor you're testing fail and go open circuit, because then the regulator will try to power the load, which is a low resistance. Okay, so that's why the fuses are there. So it occurred to me that all this circuitry on here is only passing at the most 1 amp. Okay, and a better way to build this would be to make a PCB like this. Okay, holes where the switches go, hole for this switch, holes for these banana sockets. Okay, and we could also mount the fuse holders on here as well. Okay, the terminal blocks can be mounted onto this heatsink. Yeah, and then all this bit of circuitry can actually, if we make it surface mount, because there's only 2 resistors, I think there's 8 capacitors, there's the 2 voltage regulators, the fuses won't be on here anymore, so it's a very simple circuit. So if we make that surface mount, we can put the circuit on the back of here. We can put the circuit on the back of here. That can be powered with just the 1 amp coming in, that's all it needs. And then the main lot of wiring would go down into your terminal blocks on here and into your load on here. So it separates the low current and the high current. But this can still control the transistor we need to connect to the base of each one. Okay, so if we did that, we can have all the switches mounted on here, the fuse holders, the power connection, and the regulator circuit on the back. And then it should be easy to mount your PCB onto the heatsink somewhere, however you want to mount it. We'll put some mounting holes, and we can label these up nicely, and they'll all be properly in line. I mean, you know, I kind of threw this together, got that in the wrong place and such like. But it means we can have on a silk screen on here, explains, you know, what all the connections are. Yeah? So that's the idea. So let's try this one, and then the schematic will stay the same. I will just redesign the PCB as a kind of holder for all these switches and connectors, which won't actually electrically be connected to the regulator on here. It'll still be wired directly into the load. It just allows us to mount everything much more nicely. Okay? Before we redesign the PCB then, let's test this. So we'll test a PNP transistor first. This is a TIP2955. So we'll connect this up, we'll get the data sheet, see what this can withstand, and then let's try this. To test the transistor, I have this voltmeter connected directly across the collector emitter of the transistor I want to test. This is a P-type. I have the switch set to P-type or PNP. This voltmeter is connected across the resistor. This is the first resistor I'm going to switch with the switch here, okay? And that measures the voltage across the load. Now, we don't actually need this voltmeter to test the transistor. We only need this one. So what we should see here is about 10 volts across the transistor. We can adjust that with the power supply. We can't adjust this voltage because it's set by the regulator, but we can adjust the voltage across the transistor, which effectively gives us the watts per amps. So let's power this up. And we see 10 volts across the transistor. This is set to 19. I'll just switch the load. Okay, so we have 8 volts across there, 10 across the transistor. As I say, altering the voltage here will alter the voltage on the transistor, but it won't alter the voltage on the load, at least not very much. So that's with 1 amp, and you can see the transistor is slowly warming up. Okay, so I'll just switch that off. Let's have a look to see how much current our TIP2955 can handle. So the data sheet says 15 amps. This tells us we probably need a more powerful power supply to really test these things, and some more resistors. Okay, this load will go up to 10 amps, but hopefully you would think a fake one would fail less than that. But bear that in mind, we may need more resistors and more switches basically. Or we could change the resistors, some of them to half that value, or put 2 of the 9 ohm in parallel, and then they will give 2 amps each. Yeah, we could do that, don't see why not. And then we can make a combination up of 1 amp and 2 amp. Yeah, that's probably the better way. But that is something of a moot point until I can get, say, a 20 amp supply. So we'll power this back up again. 10 volts, 8.4, 1 amp. Okay, and you can see on here 0.92 of an amp, so it's almost 1, getting on, well, towards 2. So it's not that accurate. Perhaps we should use a 8 ohm resistor to allow for the resistance of the wiring. Now notice this is at 50 degrees now, and that's up to 10 amp. well, 7.5 actually. That went up to 7.5, so that's the most I can get through there. And the temperature, well, it went up to about 90, yeah, you saw that yourself. So you shouldn't need to keep it on there for too long, particularly. Okay, you see the temperature, you see 8.2 amps. So that transistor can handle at least as much current as this can deliver, okay? If the transistor failed and say you don't need that one, you'll see the voltage here either go to 0 because the transistor's gone short, or up to whatever supply voltage on here because the transistor's gone open. Let's try an NPN transistor. So this is a TIP3055. Okay, so we have the NPN transistor on there. Once again, we'll put the temperature probe onto it. Of course, you could use a thermal camera or whatever you want, but this works well enough, I would say. Okay, so we power this on. Again, we have 10 volts across the transistor. We can adjust that if we want to get it exact, but I'm happy enough to go with close enough. Okay, so once again, we'll put some load on, 1 amp. We see a different polarity, but fair enough. And now we can start to add current again. We can see on the bench power supply, okay, the current we have 1.8. Temperature on the transistor is rising. And we can see the voltage is actually going up. See that? The transistor was getting hot, so the voltage across the transistor will actually increase as it gets hot. I'm a bit more suspicious of that one. I mean, it's not regulating as well as the PNP one did, and that's at the current I'm using 10 amp. Let's just check the datasheet for the NPN transistor. Well, it says this is for 3055 and 2955. Okay, maximum wattage is 90 watts. Well, I'm getting towards that, so I have a suspicion that transistor may not be a genuine one. Okay, I mean, it's sitting quite happily there at 3.6 amps. You can see it on the supply. It's quite hot. Okay, so we'll switch it off now. But I have my suspicion. Unfortunately, I don't have another one to test with. I'll see if I can get some more of those and we can make a comparison. Okay, the way this was behaving at 10 amps was rather like I found with fake MOSFETs at 10 amps, where the RDS would suddenly go up rapidly, yeah, whereas a good one wouldn't. And if you took it down to say about 7 amps or 6 amps, then the RDS would, obviously it will go up with temperature on the MOSFET, but it shouldn't kind of like rise very rapidly. Yeah, it's just, I suppose, test a few, you know how the good ones behave, and that's another reason why I think they are likely to be fake. But that shows the tester in operation. Let's try a MOSFET. So this is an N type MOSFET, IFPFZHDO, which should handle 12 amps continuous. Okay, and I've tried this and notice something strange. So when I pass current through this MOSFET, it makes strange sounds on my PC speakers. See if you can hear that buzzing noise. So 9 volts on the load, 9.8 on the MOSFET. We can, yeah, just over 10. And now we can start to turn that up. And do you hear the speaker? And that's handling, it only makes strange noises at certain currents. That was handling the whole thing, okay, without much of a problem at 10 amps. Guys, why the strange noise only at certain currents? Yeah. And finally, we'll test a P-type MOSFET, so IFPNOBZ. Okay, let's try this one. So 10 volts across the MOSFET, switch the load on, 811, same buzzing noise. Temperature's fine. Actually, we'll just check the current rating for this one moment. I'm assuming it is the same, but it may not be. Yeah, this is also 12 amps, okay. So, power on, 1 amp on, buzzing noise, okay, louder. And that's passing 10 amps. It's not warming up very much either, okay. Very low RDS on. Interesting, that transmission. Okay, so that appears to be a good one. Okay, so I'm happy enough that works. There are some things we need to do. So one of them is I need to get a higher rated power supply to really push these things, okay. 20 amp should be good, 20 amp 30 volts. I mean, I don't need a high voltage. And I need to do something with the resistors to allow me to test up to 20 amps. I can think of a couple different ways. So I could put, for example, a 2 ohm resistor in here that would pass 4 amps, and then change these for 4 ohm. So I'm going slightly less than half. Yeah, that'll get me probably closer to 1 amp than I was seeing on these 9 ohm resistors. So that can be 4, 6, 8, 10, 12, 14, 16, 18 amps, and then a couple of 8 ohms would give me 20. The only problem with that is this one resistor obviously would pass a lot of current, so a lot of wattage, which means that that switch is also passing a lot of current, as are the wires which are going to it, okay. Maybe better in actual fact, you know, to have 11 switches and then have 4 ohms on each one, all these 10, and having an 11th one which is 8 ohms, so they would pass 2 amps each, plus that wouldn't be 1, and then you can switch various combinations to get any ampage you want, really, between 1 and 21, okay. That might be a good way to go. So I'll play around with that, but certainly we should be able to get this driving at a higher ampage. Those of you who might have noticed, I'll just tell you this because I've got bright eyes. You see this slightly discoloured resistor here? At one point during the testing, I had the switch on the front set to N type and testing a P type transistor or PNP transistor, and it didn't work, and that resistor started to smoke after a little while. So it only smoked when I switched all the various switches on, so I was trying to put a high load on it, and it still measures 10 ohms, so it's okay, but you do need to take care to set the N and P type correctly, or at least if you've got a low resistance load, okay. So that's something to bear in mind. Another thing I noticed is that it was difficult to switch these switches with these cables on. These need to be lowered down. It just needs to be rearranged a little bit so you can get to the switches easier than I could, okay. So rearrange the layout of this, put the power in down here, put the fuses here, the PN switch, and then those further up. We can make this a bit smaller, the whole thing can come down, and just still, if I put some mounting holes in the PCB, be able to bolt it onto whatever sort of heatsink you're using. Okay, so let's redesign the PCB now. We know this thing actually works. We'll do the front panel version as I was discussing, and then I can upload that to PCBWay on the shared projects. Okay, let's get that done. And here is the schematic. It's basically the same, apart from the fuse now is mounted off the PCB, and we have a connector now which goes out to the transistor under test, so PNP emitter, PNP base, PNP collector via the fuse, okay, and ground, power, and then the NPN transistor collector via the fuse, NPN emitter, NPN base. So that's the actual schematic. This is the layout, so you can see I have put 12 switches. So these two are 1 amp, these are all 2 amp. Because I don't have the Vero board on the heatsink now, I have the space to put the 2 more resistors. So we're going to put some 4 ohm resistors in and a couple of 8 ohm resistors. This is the NPN PNP switch. I put some mounting holes on this as well, so we can mount it from the heatsink. And then you can see actually on the other side of the board is the layout for the surface mount components. I had to put a couple of vias in, a couple of tracks, so they are sort of visible on the front. But with the solder mask, you probably won't really see them. We can see a 2D view of the board here, so that's where I put the vias in. I could, I guess, have got away with that by putting some 0 ohm resistors on the back or some wire links, but I'm happy enough with it personally. And here is the 3D view, okay? So you can see the components on the rear, the two connectors, so we can plug little plugs into these and then connect them down to the load where we want them, okay? I think that's looking pretty nice. The holes here for the plus and minus supply from your bench supply, the banana sockets, that's the big switch, okay? And then this is where the fuse holders go. So what we'll do is now I will get some of these PCBs made. I will give them a final test, and if we're happy with the way it works, then I will put this as a shared project on PCBWay.com, and you can all order some PCBs yourself if you want to build this. I'd just like to thank you all for watching. Thank you PCBWay.com for sponsoring these videos. It really helps me to develop this sort of test equipment, and given the problems we do have with fake components these days, or the inability to test high powered transistors high power, this is going to be really useful, I would say. Okay, hope you enjoyed that, and I look forward to seeing you all soon again on Learning Electronics Repair. Ciao for now, guys.